In this section of physics, we're going to be looking at two-dimensional motion. We'll need to get used to a different way of writing our two-dimensional motion that you might have learned in AP Physics 1 or Physics 1. Let's start off with the definition of a position vector. That'll be the same as displacement. So let's let it equal the letter r. So what does r equal to? R equals some x coordinate multiplied by the unit vector I plus some y coordinate times the unit vector j. Now what really is the unit vector I and j? Well, think of I as the x-axis, except we're going along the x-axis a distance of only 1, or a displacement of only 1. And this number in front, or this variable in front, is a multiplier of that. So let's say x equals 2. So we're going to go 2 along the x direction vector, or the x direction axis. So twice the unit vector. So if we're a fraction, let's say this is 1/2, then we're going to go 1/2 times the unit vector, which means we'll go half along the x-axis. Same thing with j. Y is 1, then we go 1 along the y-axis. If y is 3, then we go 3 along the y-axis. So think of this vector unit here, I, as the x-axis, but a distance of only 1 along it, and this is the y-axis, but a distance of only 1 on it as well. And we'll multiply it by y and x values. So what about our instantaneous velocity that we had talked about before? How does that change with two-dimensional motion? So our instantaneous velocity, some function v sub t, is then going to equal the limit of the change in position vector with respect to the change in time. And of course, we're still going to approach delta t to 0. So what do we have now? So think of this as x and y is going to be involved with this vector here, this position vector. So it won't just be a dx dt, it's also going to be a dy as well. So we're going to write that, of course, as dr dt. And that, of course, is going to be the change in r. And what is that going to equal? The integral of dr. And then, of course, that'll be the same thing as the definite integral from t1 to t2 of v sub t dt. Okay, so we have our integration here to go backwards to get r, and of course we have our derivative to get to v. So back and forth is what we've got here. So when I integrate v sub t, I will then get r. When I take the derivative of r, I will get velocity, just like we did in the previous chapter. We will also be dealing with our x's and y's. Now what about instantaneous speed? Well, speed is just going to be equal to the magnitude of our vector. So v, or the speed, is going to be equal to v sub x, okay, squared, plus v sub y squared, all under the square root. So think of speed then as the magnitude of our vector without any direction associated with it. And that's something you've learned in the past, but we're going to look at it a little differently. So what about instantaneous acceleration? Well, it's done the same way. Acceleration versus time is then going to equal the limit of delta v over delta t as delta t approaches 0, which equals dv dt. Now remember, this is a vector, both in x and y, which is also equal to the second derivative of x with respect to t. Now remember that x means displacement now. And of course, back and forth, delta v equals the integral of dv, which equals the definite integral from t1 to t2 of our acceleration versus time. And I'll sneak a dt right here. So this is stuff that we've done in our last chapter. Except now we're going to be applying it to two-dimensional motion. Okay, so what does this practically mean? Let's take a look at it. So velocity would then have a v sub x, okay, multiplied by our vector unit, plus v sub y, multiplied by our unit for j. Remember that is the y-axis and x-axis there. And that's what we've got. So we see that velocity is comprised of an x component and a y component here. Well, we know that v does equal dr dt. So what does that look like? Well, that's going to look like this. We have to take the derivative of x with respect to t, and that of course is multiplied by the unit vector in the x direction, plus dy dt multiplied by the unit vector j. So what does this really mean? There's a x component and a y component to displacement that's changing. So what we're doing is we're taking the derivative of the x component with respect to t, and we're saying that there's also a derivative versus the y versus t. So we have two different derivatives going on here. One in the y direction, one in the x direction. Therefore, we basically end up with the same kind of idea here. V sub x multiplied by the unit vector I plus v sub y multiplied by unit vector j then equals the derivative of x with respect to t multiplied by our unit vector I plus the derivative of y with respect to t multiplied by our unit vector j. So that's how we're going to handle dealing with motion in two directions. So we have to remember then that x has nothing to do with y. These things are actually handled very, very separately. So if we have the derivative of r with respect to t, we have to remember that this is going to equal two separate things. Okay, we are then going to have v sub x, which is dx dt, and of course v sub y, which equals dy dt. So two separate derivatives that have to be handled. And of course the same thing if we have the derivative of v versus time. We have to remember that we have two separate things to deal with here. That will give us acceleration in the x direction, which equals dvx dt. And we'll have, of course, acceleration in the y, which equals dvy dt. And you've learned in AP Physics 1 that x has nothing to do with y, but it is, of course, bound by time. And of course, if we want to put any of these together, we can, what I call, Pythagorize them together. It's like this. And if we want to know angles, we can take the inverse tangent of those to get angles. And of course, the Fab 5 still apply in both directions. We just keep them separate. So for instance, if I have, the Fab 5 V final equals V initial plus AT. If I want to look at the x direction, I'll say V final x equals V initial x plus acceleration x times t. And of course t applies to both, so there's no x or y with that. We can then apply it in the y. V final in the y direction equals V initial in the y direction plus acceleration in the y direction times t. And again, we keep them separate, but we can always Pythagorize when we're done.